presentation. We're not going to let it go. We're going to give this presentation Mike because we like it. Okay.
We like
Oh, okay. So early on, I think it was both Bert and Herman talked about the importance of piping systems. In Bert's view, maybe perception, eliminate the piping, right? Eliminate it. But if you have piping, Herman is very sharp to point out that it has to be designed properly so you do not have solids being settling in your pipes. And the pictures he showed were just outstanding. I wish I had them for this presentation. So getting the piping right is super important. That means understanding design criteria for sizing pipes based on velocity, and then also calculating head losses that will allow you to set elevations and select pumps. And so that's what I'm going to go through today. I'll talk about sizing, as I mentioned, and the pressure losses for piping, also for calculating head loss through valves, just a quick exercise, and also just a real quick high-level overview of selecting pumps. Okay, so that's our objective. Nowadays, RAS come in all sorts of designs, sizes. This is a 1,000 metric ton unit at a farm in Indiana for salmon. I think the pipe sizes here in the picture were maybe 16 inches. And you'll see that they're repeated. There's a lower level and then there's an upper level. They're going to the same place. And the analysis was, well, I could combine these pipes and flows into bigger pipes and then bigger pipes, right? So you keep going bigger and bigger. But the bigger the pipe, the more expensive the pipe. And so a quick analysis showed that, well, if you just had separate runs, instead of combining all the flows into one, to create a bigger pipe, a single pipe into the drum filter, these were going to a sump. It was much, much less expensive to just do single runs. So, so the economics have to play into your piping as well, but we'll primarily focus on velocity-based pipe sizing. Of course, there's lots of smaller RAS with crazy designs like this. These are both drain flows to the sumps for treatment and then return flows to the tanks. The lower left-hand is the picture of the tank. So this was a nursery system we designed, 40 tanks. There's like 80, or two systems are identical. The total flow for the systems was pretty low. So lots of piping, lots of calculations for head loss to make sure we could flow the water. And then more moderately sized designs like this. In this case, this is a screen filter that flows to a circular sump. A couple pumps that pump it through filtration and recirc system back to the tank. So, you know, big pipes, small pipes, medium-sized pipes, they all adhere to sizing based on velocity. To prevent the solid settlement that Herman showed earlier. If you weren't in the room earlier, he showed these great pictures of pipe that had just a little bit of solid settling in them, then even more solids, to the point where it was almost completely clogged because the water velocity was so slow in the pipe that the solids just filled it up, right? So that's what you don't want. And this is so important, and I think Bert mentioned this early on, is you don't want to have, or Herman mentioned it as well, you don't want to have, I don't know what's going on here. Oh, battery. Okay. You don't want to have solids anywhere in the system that are essentially dead and rotting and mineralizing, creating excess oxygen demand and mineralizing nutrients. And if you do end up with velocities that are too low and settling in pipes, this is a real problem because excess oxygen creates places for stuff to grow, stuff like fungus. Is there something wrong with it? Okay. And it really degrades water quality. Many years ago, I visited a large hatchery that had tried full recirculation, and the engineer had sized the recirculation run back to the head of the hatchery for the worst case flow, kind of like, it was like if they had this maximum biomass and maximum feeding, he was going to have this maximum flow. Well, great, the pipe velocity would work for the maximum flow, but they didn't have the kind of water capacity to do that. So that pipe was always run at like 1/10 of the flow. So the velocity was 1/10 of what it needed to be, and thus the settling in the pipes caused tremendous fungal growth. And it was funny. I said, well, let's turn it on. Let's see what happens when we get the real flow going through it. They turn it on, and out come at the head of these raceways come these huge mats of fungus, like 1 meter, 2 meter long mats of fungus. It was disgusting. And so it was essentially rendered useless. The research system was rendered useless by the improper pipe size. So you want to make sure that you have a velocity that's moderate, doesn't cause a lot of head loss, but moves the solids through. And it's not hard, right? So 60 centimeters a second or 2 feet per second is known as a velocity that will adequately move fish waste and pretty good sized uneaten feed through the lines without settling. Okay. Now, as a designer, you may look at your charts and say, well, okay, this flow, this size pipe tells me the velocity is 1.9 feet per second. Well, you have to make a decision on whether that's acceptable. So really, there's a range around these criteria that are acceptable. And it is based on, as Herman said, your species, your feed, the local, the things that are showing you the size and type of feces you have. So we know, like for trout and salmon feces, we can vary around this 2 feet per second by 1/2 foot per second. So 1.5 feet per second will still carry the solids pretty well in the pipes. Right? But in other situations, that 1.5 could be a terrible situation where it's settling out. So really, this is our criteria. Typically, gravity flow, 2 feet per second. Keep the head loss to a minimum. Make sure the solids move through. And then this is less on keeping the solids moving through, but just on minimizing the energy you have to put into the research system with a pump by keeping your pump lines no greater than 1.5 meters per second or 5 feet per second. And now, you can use pipes that can take higher velocities. In fact, PVC can take higher velocities. But if you go to the PVC manufacturer and you check their literature, it actually says in there, do not exceed 5 feet per second. Right? So that's really where this comes from. And when I'm doing design, I'm typically sizing my pump lines for between 4 and 5 feet per second. Right? That minimizes my energy. It requires a little bit more upfront cost to make the pipes bigger. This is the energy savings is easily a cost paid back over time. So 2 feet per second on the gravity flow to move solids out, and then 5 feet per second on the pump lines. So now every thank you, Michael. Yes? No? No, it's not working. It's not working. That's okay. Okay, so and I'm sure every engineer has their own preference for pipe and specific pipe sizing. I'm not going to get into the real nitty gritty there, other than to say there are a lot of ways to do this, but it's important that you move the solids in the pipe away from settling and to your removal device, and on the energy side to keep it minimal energy losses or economical pipe costs. Okay, so the velocity. What about calculating the energy loss or the head loss? Well, there's a couple models here. I typically focus with the one Darcy Weisbach that says the head loss is equal to a function of friction, the F in that equation, times the length of the pipe divided by the diameter of the pipe, times the velocity in the pipe squared divided by 2 times the gravitational constant. So that's that. Now there's another model that you'll see from pipe manufacturers, the Hayes and Williams. I don't like this because it's not unit correct. Meaning that these exponents, while they model the friction loss, head loss correctly,